There's a star in the night sky that could explode at any moment, not in 1,000 years, but tonight. Betelgeuse, one of the brightest stars visible from Earth, is dying. When it detonates in a supernova explosion, it will be the most spectacular cosmic event witnessed in over 400 years. Bright enough to see during the day, bright enough to cast shadows at night, bright enough to change Orion forever. This isn't speculation, it's inevitable. The only question is when, and understanding what we're about to witness changes everything about how you see the sky. If watching the death of a star sounds worthwhile, a quick subscribe would mean the world to me, and drop a comment letting me know where you're watching from. Let's explore the supernova waiting to happen. To understand what's coming, you first need to know what Betelgeuse is and where to find it. If you've ever looked at the constellation Orion, you've seen Betelgeuse. It's the bright reddish star marking Orion's right shoulder, the upper left star from our perspective when we look at the constellation. Orion is one of the most recognizable patterns in the sky. 3 stars in a row make the belt. 4 bright stars form the body. Betelgeuse is one of those 4. The red one, the one that stands out because of its color. Most bright stars appear white or bluish-white. Betelgeuse is distinctly red. Even to the naked eye, you can see its reddish hue. It's beautiful, striking, different, and it's been there in the same spot for as long as humans have looked at the sky. Ancient civilizations saw it, named it, told stories about it. The name Betelgeuse comes from Arabic, though the exact translation is debated. Possibly the hand of Orion or the armpit of the giant. Either way, it's been known and observed for thousands of years. A constant in the night sky, a reliable marker, something generations of stargazers have used to navigate and to wonder. But Betelgeuse isn't just any star. It's a red supergiant, one of the largest stars we know. If you placed Betelgeuse where our Sun is, its surface would extend past the orbit of Mars. It would swallow Mercury, swallow Venus, swallow Earth, swallow Mars. We'd be inside the star. That's how enormous it is. The Sun is big compared to Earth. You could fit over 1 million Earths inside the Sun. But you could fit hundreds of millions of suns inside Betelgeuse. The scale is incomprehensible. It's not just big, it's cosmically, impossibly, mind-bendingly huge. And yet, from our perspective, 650 light-years away, it's just a bright dot in the sky. This distance, 650 light-years, is crucial. It's far enough that Betelgeuse poses no danger to us when it explodes, but close enough that the explosion will be incredibly bright, close enough that we'll see details, close enough that it will be a spectacular show. Astronomers call this the Goldilocks zone for supernova observation. Not too close to be dangerous, not too far to be dim, just right for maximum spectacle with zero risk. Betelgeuse is massive. It weighs about 15 to 20 times as much as our Sun. That might not sound like much, only 20 times. But mass makes all the difference in stellar evolution. Massive stars live fast and die young. They burn through their nuclear fuel at an incredible rate. The Sun has been burning hydrogen for about 4.5 billion years and will continue for another 5 billion, 10 billion years total. Betelgeuse formed only about 10 million years ago. In cosmic terms, it's a baby, but it's already dying, already approaching the end of its life, because massive stars don't last. They can't. They burn too hot, too bright, too fast, And now Betelgeuse has run out of hydrogen in its core. It's burning helium, then it will burn carbon, then neon, then oxygen, then silicon. Each stage lasts shorter than the last. The silicon burning stage, the final stage before explosion, lasts only a few days. Once a star starts burning silicon, the end is imminent. We don't know what stage Betelgeuse is in. It might be burning helium, it might be burning carbon, it might be in silicon burning right now. We can't tell from this distance. All we know is it's close, very close, and once it reaches that final stage, once silicon burning begins, the clock is ticking. Days, maybe a week, then boom. Let's talk about why massive stars explode, because understanding the mechanism helps you appreciate what's about to happen. Stars are balancing acts. Gravity pulls inward, trying to crush the star. Radiation pressure from nuclear fusion in the core pushes outward, trying to expand the star. These forces balance. The star remains stable. For most of a star's life, it's fusing hydrogen into helium in its core. This produces enormous amounts of energy. The radiation pressure from this energy holds the star up against gravity. But eventually, the hydrogen in the core runs out. No more fuel, no more fusion, no more radiation pressure. Gravity starts to win. The core contracts. As it contracts, it heats up. Eventually, it gets hot enough to fuse helium into carbon and oxygen. This new fusion produces energy. Radiation pressure increases. The star stabilizes again, but at a higher temperature and with the outer layers expanded. This is why Betelgeuse is so big. Its core is contracting and heating. Its outer layers are expanding and cooling. The star has become a red supergiant. This process continues. After helium burning, the core contracts again, heats up, starts burning carbon into neon and magnesium, then neon into oxygen and magnesium, then oxygen into silicon and sulfur, then silicon into iron. Each stage is faster than the last because each stage produces less energy per fusion reaction. Hydrogen burning lasts millions or billions of years. Helium burning lasts hundreds of thousands to millions of years. Carbon burning lasts thousands of years. Neon burning lasts a few years. Oxygen burning lasts months. Silicon burning lasts days. The star is racing toward its end, accelerating. The core developing a layered structure like an onion, an iron core surrounded by a shell of silicon, surrounded by oxygen, surrounded by neon, surrounded by carbon, surrounded by helium, surrounded by hydrogen. Each layer burning, producing heat, adding to the iron core at the center. And iron is the end. You can't fuse iron and get energy. Iron is the most stable nucleus. Fusing iron costs energy instead of producing it. So, when the core becomes pure iron, fusion stops. Completely. The radiation pressure vanishes, and gravity has nothing opposing it. What happens next happens fast. Unimaginably fast. The iron core, about the size of Earth but weighing about 1.5 times what the Sun weighs, collapses in less than a second. One moment it's the size of Earth. The next moment it's the size of a city, 10 kilometers across. The density becomes incomprehensible. A teaspoon of the collapsed core weighs as much as a mountain. The electrons are crushed into the protons, forming neutrons. The entire core becomes one giant atomic nucleus, a neutron star. The collapse releases enormous amounts of gravitational potential energy. This energy has to go somewhere. It goes into neutrinos. Trillions upon trillions of neutrinos blast outward. Most of them pass through the star like it's not even there. But some a tiny fraction, deposit their energy into the outer layers. This heats the material, creates an outward shock wave. The shock wave blows the outer layers of the star into space at 10% the speed of light. This is the supernova, the visible explosion, the light show, and it's powered not by the core collapse itself, but by the tiny fraction of neutrino energy that gets deposited in the outer layers. 99% of the energy from the collapse goes into neutrinos that escape unnoticed. Only 1% creates the visible explosion, but that 1% is enough to outshine an entire galaxy. The brightness of a supernova is staggering. For a few weeks, Betelgeuse will shine as bright as the full moon, maybe brighter. It will be visible during the day. You'll be able to see it in broad daylight if you know where to look. At night, it will be the brightest object in the sky after the moon, brighter than Venus, brighter than Jupiter, brighter than anything. It will cast shadows, not strong shadows like the moon, but noticeable. You'll see your shadow from starlight. That's never happened in modern history. The last supernova visible to the naked eye was in 1604, Kepler's supernova. It was in our galaxy, but farther away than Betelgeuse will be. It wasn't as bright. Before that, Tycho's supernova in 1572. And before that, the supernova of 1054 that created the Crab Nebula. 3 naked eye supernova in the last 1,000 years. All distant, all dimmer than Betelgeuse will be. Betelgeuse will be the closest, brightest supernova visible from Earth in recorded history. The brightest in over 1,000 years. Maybe the brightest in several thousand. It's going to be spectacular. The color will be striking. Supernovae are blue-white at their peak, incredibly hot. The explosion heats the ejected material to temperatures of tens of thousands of degrees. This produces blue-white light. So Betelgeuse, currently a red star, will suddenly turn blue-white, blazingly bright. Then over the course of weeks, it will fade. The color will shift from blue-white to yellow to red as the ejected material cools and expands. The brightness will decrease, slowly at first, then faster. After a few months, it might fade below naked eye visibility. You'll need telescopes to see it, but for those first few weeks, it will dominate the night sky. It will be all anyone talks about. News coverage, social media, everyone looking up, pointing, witnessing, because it's not every day a star explodes. It's not every century. It's a rare, precious, extraordinary event. And if it happens in our lifetime, we'll be among the lucky few humans to ever witness such a thing. But when will it happen? That's the question everyone wants answered. And the frustrating truth is, we don't know. Betelgeuse could explode tonight. It could explode while you're listening to this. Or it could wait another 100,000 years. The uncertainty comes from several sources. First, we don't know exactly how old Betelgeuse is. We think it's about 10 million years old, but it could be 8 million, could be 12 million. That uncertainty matters. Second, we don't know its exact mass. Is it 15 solar masses? 20? Somewhere in between? The mass determines how long each burning stage lasts. Third, we don't know what stage of fusion it's currently in. Is it burning helium, carbon, oxygen? We can't tell from our observations. The star is too far away and too shrouded in its own ejected material for us to see into the core. All we can see is the outer layers, and they don't tell us what's happening deep inside. Fourth, stellar models are imperfect. We understand the basic physics of stellar evolution, but The details are complex: turbulent convection, rotation, magnetic fields, mass loss. All of these affect how quickly a star burns through its fuel. Our models have uncertainties. They give ranges, not precise predictions. What we can say is that Betelgeuse is in the final stages of its life. It's somewhere in the red supergiant phase. It's burning something heavier than hydrogen in its core. It will explode. The question is, when? Some astronomers think it could be soon, within the next 10,000 years. Maybe even the next 1,000. Others think it has more time, maybe 100,000 years. Both camps agree on one thing: Betelgeuse is on the verge of supernova by cosmic standards, and that verge might include right now. It might have already exploded. Remember, Betelgeuse is 650 light-years away. The light we see from Betelgeuse left the star 650 years ago, in the year 1374, the late Middle Ages on Earth. The Black Death had just ravaged Europe. The Ming dynasty was beginning in China. The Aztec Empire was forming in Mexico. That's when the light we see tonight started its journey. If Betelgeuse exploded in the year 1400, we wouldn't know yet. The light from the explosion wouldn't reach us until 2050. If it exploded in 1800, we'd see it in 2450. If it exploded last year, we'd see it in about 649 years from now. We have no way of knowing if it's still there right now or if it's already gone. We won't know until the light arrives, or more precisely, until the neutrinos arrive. Because neutrinos travel at nearly the speed of light and they escape the star hours before the light from the explosion reaches the surface. When Betelgeuse explodes, neutrino detectors on Earth will see the burst before the light reaches us. This will give astronomers a few hours warning, time to point every telescope on Earth and in space at Betelgeuse, time to prepare, time to watch the explosion unfold in real time. It will be the most observed astronomical event in history. In 2019 and 2020, Betelgeuse did something unusual. It dimmed significantly. Over the course of a few months, it dropped to about 40% of its normal brightness. This was noticeable even to casual observers. If you knew where to look, Betelgeuse was visibly dimmer than usual. Astronomers got excited. Was this it? Was Betelgeuse about to explode? Social media lit up with speculation. News articles declared the supernova imminent. People started checking the sky every night, waiting, watching. But then Betelgeuse brightened again. Over a few more months, it returned to normal brightness. The supernova didn't happen. What caused the dimming? Turns out it was a combination of two factors. First, Betelgeuse is a variable star. Its brightness naturally fluctuates over time. It has multiple overlapping cycles of brightness variation. Sometimes these cycles align and the star dims more than usual. Second, Betelgeuse ejected a massive cloud of dust. Red supergiants shed material. They're so big and their gravity at the surface is so weak that material flows off them into space. Sometimes this material condenses into dust. The dust blocks light, makes the star appear dimmer from our perspective. In 2019, Betelgeuse ejected an unusually large dust cloud. This combined with a natural dimming cycle. The result was a dramatic drop in brightness. But it wasn't a sign of imminent explosion. It was just the star doing what red supergiants do, being variable, ejecting dust. The dimming event was a false alarm, but it illustrated something important. We don't fully understand Betelgeuse's behavior. We can't predict when it will explode. We can only watch, wait, and be ready. Scientists monitor Betelgeuse constantly. Multiple telescopes observe it regularly. Optical telescopes track its brightness and color. Infrared telescopes peer through the dust to see the surface. Radio telescopes map the surrounding material. Space-based observatories watch for changes we can't see from the ground. And neutrino detectors wait for the telltale burst that will signal the core collapse. These neutrino detectors are buried deep underground. Super Kamiokande in Japan, Ice Cube in Antarctica, SNO in Canada. They're watching for neutrinos from supernovae anywhere in our galaxy. When Betelgeuse explodes, these detectors will see a sudden spike in neutrino counts, an unmistakable signal. Within minutes, automated systems will alert astronomers worldwide. This is the Supernova Early Warning System, SNEWS, Supernova Early Warning System. A network of neutrino detectors linked together. When multiple detectors see the same neutrino burst, SNEWS sends out an alert. Astronomers get paged. Telescopes automatically slew to the coordinates. Observing campaigns activate. Within an hour, every major telescope on Earth will be pointed at Betelgeuse. Watching, recording. This coordination is crucial because the first hours of a supernova are critical. That's when we learn about the shockwave breakout. When we see the explosion emerge from the surface of the star, it's a brief, violent, incredibly informative phase. And we've never caught it before. Every supernova observed so far was discovered after shock breakout. We saw the explosion hours or days later. With Betelgeuse, we'll see it from the beginning, from the first light. This will revolutionize our understanding of how supernovae work. There have been a few supernovae in recorded history that people saw without telescopes. The supernova of 1054 appeared in the constellation Taurus. Chinese astronomers recorded it. They called it a guest star. It was visible during the day for 23 days, visible at night for nearly 2 years. The remnant of that explosion is the Crab Nebula, a beautiful, expanding cloud of gas and a rapidly spinning neutron star at the center, a pulsar. We can still see the nebula today, growing, expanding, evidence of an explosion that happened almost 1,000 years ago. In 1572, Tycho Brahe observed a supernova in Cassiopeia. Tycho's supernova. He studied it carefully, measured its position, noted that it didn't move relative to the stars. This proved it was not a comet or planet, but something far beyond the moon. This challenged the Aristotelian view that the heavens were perfect and unchanging. If stars could appear and disappear, the heavens were not eternal. They were dynamic, changing. The observation helped pave the way for modern astronomy. In 1604, Johannes Kepler observed another supernova, Kepler's supernova, also in our galaxy, the last naked-eye supernova in the Milky Way, over 400 years ago. Since then, nothing. We've observed plenty of supernova in other galaxies, distant explosions, faint, requiring telescopes, but none in our own galaxy visible to the naked eye. We're overdue. Statistically, a supernova should occur in the Milky Way every 50 to 100 years. We're well past that. Betelgeuse might be the one that breaks the drought. In 1987, a supernova occurred in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, SN 1987A. It was visible to the naked eye from the southern hemisphere, the first naked-eye supernova since 1604. Astronomers around the world scrambled to observe it. telescopes, neutrino detectors, everything pointed at it, and it delivered. The neutrino burst was detected, confirming the core collapse model. The light curve matched predictions. The spectrum showed the expected elements: hydrogen, helium, oxygen, the expanding shell of debris. Everything fit the theory. SN 1987. A was a triumph of astrophysics. It validated decades of theoretical work, proved that we understood how massive stars die. But it was distant, 160,000 light-years away, in another galaxy. The light was dim compared to what it would have been if the star were closer, and it was only visible from the southern hemisphere. Half the world couldn't see it. Betelgeuse will be different, visible from almost everywhere on Earth, close enough to be bright, close enough to study in detail. It will be SN 1987A, but better, much better. The supernova of a lifetime, maybe the supernova of several lifetimes, an event that will be remembered and studied for centuries. The mechanics of a supernova are worth understanding in more detail because they reveal just how violent and energetic these events are. When the iron core collapses, the process is catastrophic. Imagine the mass of 1.5 suns compressed from the size of Earth to the size of Manhattan in less than a second. The speed of the collapse approaches a significant fraction of the speed of light. Material at the edge of the core is falling inward at thousands of kilometers per second. This is faster than the speed of sound in the material. So, the material can't send pressure waves ahead to warn the outer layers what's coming. It's a supersonic collapse. The outer layers have no idea the core is collapsing until the collapse stops abruptly when the core reaches nuclear density and can't be compressed further. At that point, the infalling material bounces. It rebounds off the incompressible neutron core. This rebound creates a shock wave that propagates outward through the star. This shock wave should, in theory, blow the star apart immediately, but simulations show that the shock wave stalls. It gets stuck a few hundred kilometers from the center. The shock loses energy trying to push through the dense material still falling inward. It doesn't have enough momentum to break through. This is where neutrinos save the day. During the core collapse, enormous numbers of neutrinos are created. When electrons combine with protons to form neutrons, they also produce neutrinos. The collapsing core produces about 10 to the 57 neutrinos in a few seconds. That's a 1 followed by 57 zeros, an incomprehensible number. Most of these neutrinos escape immediately. They don't interact with anything. They pass through the star and fly off into space. But some, a tiny fraction, maybe 1 in 10 billion, interact with the material behind the stalled shockwave. They deposit energy, heat the material, increase the pressure. This revives the shockwave, gives it the extra push it needs to blow through the star. The shock propagates outward, accelerating, heating the material as it goes. When it reaches the surface of the star, the shock breaks out. The star suddenly becomes incredibly bright. This shock breakout is one of the most energetic events in the universe. For a few minutes, the shock breakout can be as luminous as an entire galaxy. Then the expanding fireball begins to cool and the supernova enters its peak brightness phase. The light we see from a supernova comes primarily from radioactive decay. When the shock wave passes through the star, it heats the material to billions of degrees. At these temperatures, nuclear reactions occur, silicon fuses into nickel-56, a radioactive isotope. The expanding fireball contains about 1/10 of a solar mass of nickel-56. This nickel decays to cobalt-56 with a half-life of 6 days. The cobalt then decays to stable iron-56 with a half-life of 77 days. These decay processes release energy, gamma rays. The gamma rays heat the expanding material, make it glow. This is what we see, the expanding, glowing, radioactively heated debris. The brightness peaks a few weeks after the explosion when the expanding material becomes optically thin. Before that, the material is so dense that photons can't escape. They get absorbed and re-emitted multiple times. They're trapped. But as the material expands, it thins. Eventually, photons can escape. That's when we see peak brightness. After that, the brightness decays as the radioactive material runs out. Cobalt-56 decays away. The energy source diminishes. The supernova fades. The light curve, a plot of brightness versus time, follows the decay rate of cobalt-56. This is how we know radioactive decay powers the visible light. The observed light curve matches the predicted decay curve almost perfectly. Understanding this mechanism explains why supernovae look the way they do and why they're so bright. A supernova releases about 10 to the 44 joules of energy. Most of that goes into neutrinos. About 1%, 10 to the 42 joules, goes into the kinetic energy of the expanding debris. And about 0.01%, 10 to the 40 joules, goes into visible light. But even that tiny fraction is enormous. 10 to the 40 joules is equivalent to the sun's entire energy output over its 10 billion year lifetime, all released in a few weeks. That's why supernovae are so bright. They're dumping the equivalent of a star's lifetime energy into space in weeks. At peak, a supernova can outshine its entire host galaxy, a single star brighter than 100 billion stars combined. It's one of the most powerful events in the universe short of a gamma ray burst or the merger of black holes or neutron stars. When Betelgeuse explodes, all of this will happen. The iron core will collapse. Neutrinos will burst outward. The shock wave will propagate. The star will brighten. And we'll see it unfold over weeks. But we'll also see something unprecedented. We'll see the neutrino burst before the light arrives. This is because neutrinos escape from the core collapse immediately. They don't wait for the shock to reach the surface. They leave the star hours before the light does. The shock has to plow through the star's outer layers. This takes time, maybe 4 to 12 hours for a star like Betelgeuse. During those hours, the core has already collapsed. The neutron star has formed. The neutrinos have escaped, but the surface hasn't reacted yet. It doesn't know anything has happened. Then the shock arrives, breaks out, and suddenly the star brightens. But the neutrinos are already here. They arrive hours earlier. This early warning is invaluable. It gives astronomers time to point every instrument at Betelgeuse before the light show begins. Time to prepare, time to coordinate, time to make sure nothing is missed. The neutrino burst from Betelgeuse will be detected by multiple facilities simultaneously. Super Kamiokande in Japan is a huge tank of ultra-pure water buried a kilometer underground. When a neutrino interacts with water, it produces a flash of light. Detectors around the tank see the flash, record it. Each neutrino interaction creates a distinctive signal. During the core collapse of Betelgeuse, Super Kamiokande will see dozens, maybe hundreds of neutrino events over a few seconds. This is vastly more than the usual background rate of a few events per day. It's an unmistakable signal. Ice cube in Antarctica is even larger. It uses a cubic kilometer of Antarctic ice as the detector. Neutrino interactions in the ice create light. Sensors frozen into the ice detect it. Ice cube sees neutrinos from the entire sky. When Betelgeuse explodes, Ice cube will see a burst. SNO, the Sudbury Neutrino Observatory in Canada, also watches for supernova neutrinos using heavy water as a detector. Together, these facilities form a neutrino early warning network. When they all see the same burst within seconds of each other, it's confirmation. A supernova has occurred, and based on the arrival time differences between detectors, astronomers can triangulate the source, figure out which star exploded. For Betelgeuse, this will be easy. It's the only massive star close enough and well known enough to produce such a strong neutrino signal. The alert will go out immediately. Betelgeuse. It's happening. Imagine the moment. You're an astronomer, maybe working on something completely unrelated, analyzing data, writing a paper, teaching a class. Then your phone buzzes, an automated alert. Snooze, supernova, detection, Betelgeuse. Your heart races. This is it. The event you've been waiting for your entire career. The event humanity has been waiting for over 400 years. You drop everything, log into the telescope scheduling system, submit an urgent target of opportunity request, Betelgeuse, maximum priority. Within minutes, telescopes around the world are slewing, moving, pointing. The largest optical telescopes, radio telescopes, infrared observatories, space telescopes. Everything that can see Betelgeuse is looking at it, waiting, recording. The surface of the star hasn't reacted yet. It still looks normal, a red supergiant, but deep inside, the core has collapsed. The shock is propagating outward. In a few hours, maybe 6 or 8, the shock will break out, and when it does, cameras will be rolling. Spectrographs recording, every wavelength monitored, the most comprehensive observation of any astronomical event ever. The first sign will be a sudden brightening. Within minutes, Betelgeuse will go from magnitude 0.5, its normal brightness, to maybe magnitude -5 or -6, increasing 100-fold, 1,000-fold. The star will become dazzling, unmissable. Reports will start flooding in from amateur astronomers, people who just happen to look at Orion. They'll see Betelgeuse blazing, brighter than anything in the constellation, brighter than anything except the moon. News will spread instantly, social media, news websites. Everyone will know within an hour. The supernova has begun. Go outside, look at Orion, see the dying star, and millions of people will. They'll step outside, look up, and there it will be. A brilliant news light in the familiar constellation, something that wasn't there yesterday, something that will change how Orion looks for the rest of their lives. This is the moment that connects humanity across cultures and generations. Everyone alive when Betelgeuse explodes will remember it. Where they were, who they were with, what they felt. It will be a shared experience, a collective moment of wonder, like the first moon landing, like major historical events that define an era. The Betelgeuse supernova will be one of those moments. The cultural impact will be profound. Orion is one of the most important constellations in human history. It's visible from almost everywhere on Earth. It's recognizable, unmistakable. 3 stars in a row make the belt. Everyone knows Orion. For thousands of years, cultures around the world have told stories about this pattern. The ancient Egyptians associated Orion with Osiris, god of the afterlife. The stars of Orion's belt align with the pyramids of Giza. The Greeks saw Orion the hunter, a figure from their mythology. The Aboriginal Australians saw a canoe. The Inuit saw a group of hunters. Native American tribes had their own interpretations. The constellation has been a constant, a familiar friend in the night sky. Generations of sailors used it for navigation. Farmers used it to mark seasons. Poets wrote about it. Artists painted it. And now it's going to change. When Betelgeuse explodes, Orion will never look the same. Instead of the red star at the shoulder, there will be a brilliant blue-white beacon. Then, as the supernova fades over months, that beacon will dim, eventually disappear. Orion will have 3 bright stars instead of 4. The shoulder will be gone, the pattern altered. This change will be permanent. For the rest of human history, Orion will look different. The constellation we grew up with will be a memory. Our grandchildren will never see the Orion we knew. They'll see a different pattern, and they'll tell different stories. The star that exploded, the supernova our ancestors witnessed. It will become part of the mythology, the lore, the living history of humanity's relationship with the sky. Astronomers will study the supernova remnant for decades, centuries. The expanding cloud of debris will grow. Year by year, it will get larger. The material will spread into space, carrying with it the elements forged in Betelgeuse's core and in the explosion itself. Oxygen, silicon, iron, nickel. All the heavy elements. These elements will enrich the interstellar medium, become part of the next generation of stars and planets. This is how the universe works. Stars like Betelgeuse create heavy elements. They explode, the elements spread, new stars form from the enriched material. Those stars host planets. Those planets might support life. We're made of star stuff, the calcium in our bones, the iron in our blood, the oxygen we breathe. All of it was forged in stars that exploded billions of years ago. Betelgeuse will continue this cycle. Its debris will eventually contribute to new worlds, new possibilities. Maybe someday, billions of years in the future, intelligent beings on a planet formed from Betelgeuse's remnants will look at their sky and wonder about the stars. They won't know their world is made from the ashes of a supernova. But it will be, and in a way, Betelgeuse will live on, not as a star, but as the substance of planets and life and consciousness spread across the cosmos. The neutron star left behind by Betelgeuse's explosion will be fascinating. Neutron stars are the densest objects in the universe that aren't black holes. A neutron star with the mass of 1.5 suns compressed into a sphere maybe 20 kilometers across. A teaspoon of neutron star material weighs as much as a mountain. The density is beyond comprehension, and the physics is exotic. The surface gravity is enormous, about 100 billion times Earth's gravity. If you could somehow stand on a neutron star, you'd be crushed instantly, flattened to atomic thickness. The magnetic field is intense, trillions of times stronger than Earth's, and the rotation is fast. Neutron stars spin, often many times per second. Some pulsars, which are rotating neutron stars that emit beams of radiation, spin hundreds of times per second. The rotation comes from conservation of angular momentum. When the core collapses, it shrinks. Just like a spinning ice skater pulling in their arm spins faster, a collapsing stellar core spins up dramatically. The result is a rapidly spinning, incredibly dense, absurdly magnetic object. A neutron star. Betelgeuse's neutron star might become a pulsar. If the magnetic field is aligned right and the rotation is fast enough, we might see regular pulses of radiation as the neutron star's beam sweeps past Earth. Like a cosmic lighthouse. Pulsars are incredibly useful for astronomy. Their pulses are regular, precise. You can use them as clocks. Some pulsars are so stable they rival atomic clocks in precision. Astronomers use pulsars to test general relativity, to detect gravitational waves, to probe the interstellar medium. If Betelgeuse produces a pulsar, it will become one of the closest, brightest pulsars known. A valuable tool for research, a window into extreme physics. But it's also possible the neutron star won't be a pulsar. Maybe the magnetic field isn't aligned correctly. Maybe the rotation isn't fast enough. In that case, the neutron star will be there, sitting in the center of the expanding debris cloud. But we won't see pulses. It will be a quiet neutron star. Still interesting, still worth studying, but less dramatic than a pulsar. There's even a small chance Betelgeuse will form a black hole instead of a neutron star. If the core is massive enough, greater than about 2 or 3 solar masses, the neutron star can't support itself. Neutron degeneracy pressure, the quantum mechanical force that holds neutron stars up against gravity, has a limit. Beyond that limit, nothing can stop the collapse. The neutron star collapses further, becomes a black hole. For Betelgeuse, this depends on how much mass falls back onto the neutron star after the initial explosion. If a lot of material falls back, the neutron star might exceed the mass limit and collapse into a black hole. We won't know until it happens. The neutrino burst will tell us the core has collapsed. The light curve will tell us the explosion occurred. But figuring out whether the remnant is a neutron star or a black hole will take years of observation, watching the center of the expanding debris. Looking for a pulsar. If we find one, it's a neutron star. If we don't, it might be a quiet neutron star, or it might be a black hole. Distinguishing between these will require careful study, but that's part of the excitement. We'll learn, we'll figure it out, and whatever we find will teach us about the endpoints of stellar evolution. Let's talk more about the visual experience of watching Betelgeuse explode, because this is something that will define the event for most people. Imagine stepping outside on a clear night a few hours after the neutrino burst. News has spread. Astronomers have announced it. Social media is exploding with posts. Everyone's talking about it. You walk outside, look up at Orion, and there it is. Where Betelgeuse used to be a reddish star of moderate brightness, there's now a blazing blue-white point of light. Stunningly bright, brighter than any star you've ever seen, brighter than Venus at its brightest, maybe as bright as the quarter moon. It doesn't twinkle like stars do. It's too bright for atmospheric scintillation to affect it noticeably. It just shines. Steady, brilliant, overwhelming. The rest of Orion is still there, the belt, Rigel, but Betelgeuse dominates. It's all you see. You can't look away. This brilliant new light that wasn't there yesterday. And you realize you're watching something that hasn't happened in recorded history. The explosion of a nearby massive star, right there in the most famous constellation, visible to everyone on Earth who can see Orion. No telescope needed, no special equipment, just eyes. and a clear sky. During the day, if you know where to look, you'll be able to see it. This is extraordinary. Stars aren't visible during the day. The sky is too bright, but Betelgeuse at peak will be bright enough to see. You'll have to shield your eyes from the sun. Look in the direction where Orion would be if you could see it. And there, faint against the blue sky, will be a point of light. The supernova, visible in daylight. This hasn't happened since Kepler's supernova in 1604, which was reportedly visible during the day. And that was farther away and dimmer than Betelgeuse will be. Seeing a star in daylight will be surreal, unnatural, wrong in a way that makes your brain struggle to process it. But there it will be. Proof that the universe doesn't care about our expectations. Proof that extraordinary things happen, that we're living through one of those things. At night, the supernova will cast shadows. Not strong shadows like the full moon, but detectable. If you're in a dark area, away from city lights, and you hold up your hand, you'll see a faint shadow cast by the supernova. This is unprecedented in living memory. No star has been bright enough to cast shadows since ancient times. Maybe the supernova of 1054 did, maybe earlier ones, but no one alive has experienced it. It will be strange, eerie, beautiful, and it will only last a few weeks. After peak brightness, the supernova will begin to fade. Over the course of a month or two, it will drop in brightness. Still visible, still impressive, but diminishing. After a few months, it might drop below naked eye visibility. You'll need binoculars or a telescope to see it. But during those first weeks, it will be impossible to miss. Everyone will see it. Everyone will talk about it. It will be the biggest astronomical event in modern history. Bigger than the moon landing because you don't need a TV to see it. You just need to look up. Bigger than eclipses because it's not over in minutes. It lasts for weeks. Accessible to everyone, everywhere. A shared global experience. Photographers will have a field day. Imagine the images. Orion with Betelgeuse blazing. Long exposure shots showing the constellation in a way it's never been photographed before. The supernova will outshine everything. Wash out the other stars. Photographers will have to adjust their exposure settings to avoid oversaturating the supernova. And they'll capture images that become iconic, historical. The Betelgeuse supernova seen from Earth, from cities, from deserts, from mountains, from every part of the globe. These images will be preserved, studied, shown in textbooks and documentaries for centuries. Future generations will look at them with envy, wishing they'd been alive to see it. Just like we look at historical supernova records and wish we could have witnessed them. The Betelgeuse supernova will be our generation's contribution to astronomical history. Our moment, our witness. The scientific value of observing Betelgeuse explode cannot be overstated. We've observed many supernovae, thousands of them in distant galaxies. We have a good theoretical understanding of how they work, but we've never observed one this close, never had the opportunity to study one in such detail. Betelgeuse will give us that chance. We'll be able to measure things we've never measured before, the composition of the ejected material with incredible precision. We'll see individual elements, isotopes. We'll track how the material mixes as it expands. We'll watch the shock wave evolve, see how it interacts with the material Betelgeuse ejected before the explosion. Red supergiants shed mass. They create a cocoon of gas and dust around themselves. When the supernova shockwave hits this cocoon, it will light it up. We'll see the cocoon glow. This will teach us about mass loss in the final years of a massive star's life. How much mass do they lose? How fast? In what directions? These are questions we can only partially answer with distant supernovae. With Betelgeuse, we'll have ringside seats. We'll see everything. We'll also test our theories. Does the explosion match predictions? Does the light curve follow the expected shape? Does the spectrum show the expected elements at the expected abundances? Are there surprises, anomalies, things we didn't predict? Almost certainly yes. Every time we observe a supernova closely, we learn something unexpected. SN 1987. It taught us that blue supergiants can explode, not just red ones. It showed us that pre-supernova mass loss shapes the environment and affects how we see the explosion. Betelgeuse will undoubtedly surprise us too. Maybe the explosion will be asymmetric, stronger in one direction than another. Maybe the light curve will have unexpected bumps or dips. Maybe the spectrum will show unusual elements or unexpected abundances. Whatever we find will refine our models, push our understanding forward. This is how science works. We predict, we observe, we compare, we learn, and we improve our theories. Betelgeuse will be a masterclass in this process, a real time test of stellar evolution theory watched by astronomers worldwide. The timing of the supernova matters for more than just when we see it. It also affects what we learn. If Betelgeuse explodes soon, within the next few years or decades, we'll observe it with current technology. Ground-based telescopes, space telescopes like Hubble and James Webb, radio telescopes like ALMA and the VLA. These are powerful instruments. They'll gather excellent data, but if Betelgeuse waits, if it explodes 100 years from now, we'll observe it with future technology. Telescopes we haven't built yet, technologies we haven't invented. The data will be even better, more detailed, more comprehensive. There's a tension here. Astronomers want Betelgeuse to explode soon because they want to see it. They want to study it with the tools they have now. They don't want to wait. But from a pure scientific perspective, waiting might yield better data. Of course, we have no control over this. Betelgeuse will explode when it explodes. We just have to be ready. And we are. The infrastructure is in place. The detectors are running. The plans are made. When it happens, we'll observe it as thoroughly as possible with whatever tools we have at that moment. And we'll learn, and we'll be grateful for the opportunity. There's something deeply moving about the fact that Betelgeuse is dying. Stars aren't supposed to feel temporary. They're so long-lived compared to us. They're constants, reliable, eternal from a human perspective. But they're not eternal. They're born, they live, they die. Betelgeuse has been visible in the sky for all of human history. Ancient humans saw it. Early civilizations saw it. Every generation of humans has seen Betelgeuse. It's been a constant companion, a reliable marker in the night sky. But soon it won't be there anymore, not as a star. It will be gone, transformed into a neutron star or black hole surrounded by an expanding cloud of gas. This transformation is natural, inevitable. Stars don't last forever. And in Betelgeuse's case, the end is near, very near. We're living in the final moments of Betelgeuse's existence as a star. The last generation, or one of the last, to see it as a red supergiant. This makes our time special. We're witnessing the end of an era, the death of a star that has been a companion to humanity for all of our existence. That's profound. That's moving. And it reminds us that nothing lasts forever, not even stars. But Betelgeuse's death is also a beginning. The material it ejects will spread into space, enrich the interstellar medium, become part of future stars and planets. The explosion will trigger star formation in nearby clouds of gas. The shock wave will compress the gas, cause it to collapse, form new stars. These stars will be children of Betelgeuse, born from its death. And maybe some of those stars will have planets. Maybe some of those planets will have life. Maybe intelligent life, beings who will look up at their sky and wonder about the stars, never knowing they owe their existence to a supernova that happened billions of years before. This is the cycle of stellar life and death. This is how the universe renews itself, recycles material, creates new possibilities. Betelgeuse's death isn't an ending, it's a transformation, a continuation. The star's material will persist, will become other things, will participate in the ongoing story of the cosmos. That's beautiful, that's hopeful, that's the universe at its most creative and resilient. The Betelgeuse supernova will inspire people, not just astronomers, but everyone. Artists will create works inspired by the explosion. Musicians will compose pieces. Poets will write. The supernova will become a cultural touchstone, a symbol of change, of impermanence, of cosmic scale, of our connection to the universe. People will remember where they were when it happened. They'll tell their grandchildren, "I saw Betelgeuse explode. I was there. I witnessed it." This shared experience will bind people together, across cultures, across borders, across generations. Everyone will have seen the same thing. Everyone will have been touched by the same event. In a world often divided, the supernova will be a unifying moment, a reminder that we're all on the same planet, looking at the same sky, part of the same universe, subject to the same laws of physics, connected by our curiosity and wonder. That's powerful, that's important, that's one of the gifts Betelgeuse will give us. Not just scientific knowledge, but cultural cohesion, a shared story, a common experience, something that belongs to all of humanity. There's one more aspect of Betelgeuse worth contemplating, and that's the sheer scale of what's about to happen. When the core collapses, it releases more energy in a few seconds than the sun will release in its entire 10 billion year lifetime. Most of that energy goes into neutrinos. But even the tiny fraction that goes into the visible explosion is staggering. The explosion will hurl several solar masses of material into space at 10,000 kilometers per second. That's 3% the speed of light. Imagine several suns worth of matter moving at 3% light speed. The kinetic energy is almost incomprehensible. If you could harness that energy, you could power human civilization at current levels for billions of years. The explosion will create temperatures of billions of degrees. At these temperatures, nuclear reactions create elements that don't exist anywhere else in nature. Radioactive isotopes, exotic nuclei, things that decay almost immediately. The periodic table comes alive in a supernova. Every element heavier than iron is created in the explosion or in the aftermath. Gold, platinum, uranium, all forged in supernovae. The ring you might be wearing, the electronics in your phone, the atoms in your body. Many of them came from stellar explosions like the one Betelgeuse is about to produce. This connects us to these events in a visceral way. We're not just observers, We're products of supernovae, made of star stuff, and when Betelgeuse explodes, it will be creating the building blocks for future worlds, future life, future civilizations perhaps. The cycle continues, and we get to watch this particular iteration unfold in our sky. The explosion will also be loud. Not that we'll hear it. Sound doesn't travel through the vacuum of space. But if it could, the supernova would be incredibly loud. Calculations suggest it would produce a sound level of over 200 decibels at Earth's distance. For comparison, a jet engine at close range is about 140 decibels. 200 decibels would be ear-shattering, lethal at close range. The shock wave from the sound alone would be devastating. Fortunately, the vacuum of space protects us. We'll see the explosion. We'll detect the neutrinos and the light and the radiation. But we won't hear it. Space is silent. The supernova will be a spectacular light show, a neutrino burst, a scientific bonanza, but acoustically, nothing. This strange disconnection, seeing something so violent and energetic happen in complete silence, is one of the peculiarities of astronomy. We watch cosmic events unfold across vast distances. We see collisions of galaxies, explosions of stars, jets of material shooting from black holes, all in eerie silence. The sky is a silent movie, beautiful, dramatic, but quiet. And that's fitting. It allows us to contemplate these events calmly, appreciate their majesty without being overwhelmed by the noise they would make if we were close enough to hear them. Understanding Betelgeuse and its impending explosion also gives us perspective on our own sun. The sun is a stable, well-behaved star. It's been burning hydrogen for 4.5 billion years. It will continue for another 5 billion. It won't explode. It's not massive enough. When the sun runs out of hydrogen, it will swell into a red giant, much like Betelgeuse is now. But instead of exploding, it will gently shed its outer layers. The core will become a white dwarf, a dense, slowly cooling ember. The outer layers will form a planetary nebula, a beautiful expanding shell of glowing gas, but no explosion, no supernova, no neutron star. The sun's death will be peaceful, slow. Over billions of years, the white dwarf will cool until it's no longer visible. A black dwarf, a stellar corpse. This is the fate of stars like the sun, and it's a very different fate than what awaits Betelgeuse. This difference comes down to mass. Massive stars burn hot and die violently. Low-mass stars burn cool and die gently. The sun is in the low-mass category. Betelgeuse is in the high-mass category. And because of this, Betelgeuse's end will be spectacular, a cosmic fireworks display, while the sun's end will be quiet, a slow fading. Both are natural. Both are beautiful in their own way, but they're profoundly different, and witnessing Betelgeuse's death reminds us how diverse stellar evolution can be, how different stars of different masses follow different paths, live different lives, meet different ends. This diversity is part of what makes astronomy endlessly fascinating. No two stars are exactly alike. They vary in mass, composition, age, rotation, magnetic fields. They interact with their environments differently. Some are in binary systems, locked in gravitational dances with companions. Some are isolated, alone in space. Some are surrounded by planets. Some have none. Each star is unique, has its own story, its own history, and Betelgeuse's story is about to reach its climax. The final chapter, the explosive end. We're fortunate to be here to witness it, to see this particular story unfold, to learn from it, to be inspired by it, and to carry that inspiration forward into our own lives, our own understanding of the universe, our own place in the cosmic story, because we're part of this too. We're not separate from the universe. We're in it, of it, made from the same atoms, subject to the same laws, connected to stars like Betelgeuse through chains of cause and effect that stretch back billions of years. The atoms in your body were forged in stars. Some of those stars exploded. The material spread, became part of the cloud that formed our solar system, became part of Earth, became part of you. You're literally made of stardust, and when Betelgeuse explodes, it will create more stardust, material that will billions of years from now become part of new worlds, maybe new life. The cycle continues, and we're part of it, witnessing it, participating in it. That's extraordinary, that's humbling, that's wonderful. The neutrino burst from Betelgeuse deserves even more attention because it represents something extraordinary in astronomy. When the core collapses, it happens so fast that the outer layers of the star don't have time to react. They don't know anything has happened yet. The surface is still shining normally, still radiating light like it has for millions of years. But deep inside, the core has vanished, compressed from the size of Earth to the size of a city in less than a second. And during that compression, enormous numbers of neutrinos are created and released. These neutrinos don't interact with normal matter very much. That's their defining characteristic. Most particles would get absorbed by the dense material surrounding the core. Photons, for instance, can't escape. They bounce around inside the star for hours before finally working their way to the surface. But neutrinos are different. They pass through matter like it's not even there. They stream out of the collapsing core immediately, unimpeded, racing outward at nearly the speed of light, and they arrive at Earth hours before the visible light from the explosion. This early arrival gives us a unique opportunity. When neutrino detectors around the world suddenly register a burst of neutrinos from the same direction at the same time, we know immediately that a core collapse has occurred. The star has exploded, but the light hasn't reached the surface yet. The shock wave is still propagating outward through the star's outer layers. For those few hours between the neutrino detection and the optical brightening, we have advance warning. We know what's coming. This has never been used to observe the start of a supernova before. SN 1987A was detected by neutrinos, but the optical discovery happened hours later, almost by accident. An amateur astronomer in New Zealand happened to photograph that region of the sky and noticed the new bright star. By the time professional astronomers were alerted and pointed their telescopes, the shock breakout had already happened. They missed it. With Betelgeuse, we won't miss it. The neutrino alert will go out automatically. Telescopes will slew within minutes. Cameras will be recording when the shock breaks through the surface and the star suddenly brightens. We'll capture the moment, every wavelength, every detail. It will be unprecedented. The neutrino burst itself is fascinating physics. Neutrinos come in 3 types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They can oscillate between these flavors as they travel. A neutrino that starts as an electron neutrino might arrive as a muon neutrino. This oscillation depends on the properties of neutrinos that we're still trying to understand. Their masses, how they interact. By studying the neutrino burst from Betelgeuse, we can learn about neutrino physics. How many of each flavor arrive? How does that compare to what was emitted? What does the timing tell us about neutrino properties? These are fundamental questions in particle physics, and a nearby supernova gives us a natural laboratory, an experiment we could never build on Earth. The energies involved, the densities, the temperatures, all far beyond anything we can create artificially. Nature provides the experiment. We just have to watch and measure. The neutrino burst will also tell us about the core collapse itself, the exact timing of the burst, its duration, its intensity. All of these encode information about what happened during the collapse. How fast did the core fall? How dense did it get? Was there a bounce? Multiple bounces? Did material fall back onto the proto-neutron star? These details affect the neutrino emission. By analyzing the burst, we can reconstruct what happened deep inside Betelgeuse during those critical seconds. This is forensic astronomy, using the evidence we receive to piece together events we can't see directly. And it's incredibly powerful. We're essentially doing time travel, looking back at an event that happened 650 years ago, plus the few seconds of the core collapse. But we're seeing it unfold in real time from our perspective. The light from the event is just reaching us now, so we experience it as if it's happening now, even though the actual event occurred centuries ago. This is one of the strange consequences of the finite speed of light. Distance and time become entangled. What's happening now at Betelgeuse, we won't know for another 650 years. What we see now happened 650 years ago. It's like the universe has a built-in delay, a cosmic lag. This leads to an interesting thought. If Betelgeuse has already exploded, if it blew up centuries ago, the light and neutrinos are on their way to us right now, traveling through space at light speed, crossing the 650 light years that separate us from Betelgeuse. They could arrive tomorrow, or tonight, or next week. We have no way of knowing. The star could be gone already, replaced by a neutron star and an expanding debris cloud. But we won't know until the light gets here. This uncertainty is both frustrating and exciting. Frustrating because we can't check. We can't send a signal to Betelgeuse and get a status update. Any signal would take 650 years to arrive and another 650 to return. 1,300 years round trip. Useless for immediate information. But it's also exciting because it means the supernova could happen at any moment, could already have happened. The universe is keeping a secret from us, and the secret will be revealed when the light arrives, whenever that is. Let's talk about what the supernova won't do, because there's a lot of misinformation and fear mongering about supernovae in general. Betelgeuse will not harm Earth. It won't destroy us. It won't even damage our atmosphere significantly. The distance is too great. 650 light years is far, very far. Yes, the supernova will be bright from our perspective. Yes, it will be spectacular. But brightness and danger are not the same thing. The explosion will release enormous amounts of energy. But that energy spreads out in all directions. By the time it reaches Earth, it's diluted by a factor of 1 over the distance squared. 650 light years is a huge distance. The dilution factor is enormous. What reaches us is a tiny fraction of the total energy. Enough to be bright, enough to be visible, but not enough to be dangerous. Supernovae can be dangerous if they're close. Within about 25 light years or so, a supernova could strip away Earth's ozone layer. The high-energy radiation, gamma rays, and X-rays would hit the atmosphere, ionize it, break apart ozone molecules. Without ozone, harmful ultraviolet light from the sun would reach the surface. This could damage ecosystems, cause extinctions. Some scientists think a nearby supernova might have contributed to past mass extinctions on Earth. There's evidence of radioactive isotopes in ocean sediments that could come from supernovae. Maybe a supernova 2 or 3 million years ago contributed to climate changes that affected early human evolution. But these are speculative. The evidence is suggestive, but not conclusive. And regardless, Betelgeuse is much farther than 25 light-years. It's 650 light-years away. At that distance, the radiation reaching Earth will be negligible. Our atmosphere will absorb it easily. No ozone depletion, no ecosystem damage, no danger whatsoever. We can enjoy the light show without worrying about harm. Another myth is that the supernova will somehow affect Earth magnetically or gravitationally. It won't. Magnetic fields decrease rapidly with distance. By the time you're 650 light-years away, even the strongest magnetic field is negligible. Gravity also decreases with distance. The gravitational pull from Betelgeuse on Earth is already infinitesimally small. When it explodes and becomes a neutron star or black hole, the gravitational pull will remain the same. Mass doesn't disappear, it just gets redistributed. The neutron star or black hole will have the same mass as Betelgeuse's core, just compressed into a smaller volume. But from 650 light-years away, this makes no difference. The gravitational effect on Earth is zero. We won't feel anything. Our orbit won't change. The Moon's orbit won't change. Nothing will be affected gravitationally. The supernova is a light show, a scientific opportunity, not a threat. The impact on astronomy, however, will be enormous. Every astronomer on Earth will want to observe Betelgeuse. Telescope time is usually scheduled months or years in advance. Committees review proposals, allocate hours. But supernovae are transient events. They don't wait for scheduling. So there are policies in place for target of opportunity observations. If something urgent happens, telescopes can be overridden, scheduled observations postponed. The telescope pointed at the urgent target. Betelgeuse will trigger this on a scale never seen before. Every major observatory will be affected. The Hubble Space Telescope will observe Betelgeuse. The James Webb Space Telescope will observe it. Ground-based telescopes around the world will observe it. Radio telescopes, infrared telescopes, X-ray satellites, everything. This coordination will be unprecedented. Astronomers from different countries, different institutions, different wavelengths will all be working together, sharing data, collaborating, because everyone understands the importance. This is a once-in-a-lifetime event, maybe once in several lifetimes. The data will be public, shared immediately. Everyone will have access, because the goal is not individual glory, but collective understanding. We want to learn as much as possible, and that requires everyone contributing. The data collected will keep astronomers busy for years, decades even. Every spectrum, every image, every measurement will be analyzed, compared to models used to test theories. Graduate students will write dissertations on Betelgeuse data. Careers will be built on studying this one event, and the data will remain valuable for generations. Future astronomers will revisit it. analyze it with new techniques, new understanding. The observations we make when Betelgeuse explodes will be a resource for astronomy for the rest of human history. This is how important it is. This is why astronomers are so eager for it to happen. Not just to see something spectacular, though that's certainly part of it, but to gather data that will advance our understanding of stellar evolution, supernova physics, nucleosynthesis, and a dozen other fields. Betelgeuse will be a scientific goldmine. The remnant left behind will also be studied intensely. Initially, the debris cloud will be hot and bright, glowing from radioactive decay and from the shock heating. It will expand at thousands of kilometers per second. After a few years, the cloud will have grown large enough that telescopes can resolve it. See its structure. Is it symmetric? Asymmetric? Are there clumps, jets? Does it interact with surrounding material? All of these details tell us about the explosion mechanism and the environment around Betelgeuse before it exploded. Over decades, the nebula will continue expanding, cooling. Its appearance will change, colors shifting as different elements cool and recombine. Astronomers will track these changes, build models to match observations, learn about how supernova remnants evolve. This is important for understanding other supernova remnants we see in the galaxy, old ones like the Crab Nebula. With Betelgeuse, we'll watch the evolution from the beginning, see how a freshly exploded star turns into a nebula over years and decades. No other supernova remnant gives us this opportunity. They're all old, already evolved. Betelgeuse will be fresh, new, a chance to see the process unfold. At the center of the nebula will be the neutron star or black hole. If it's a neutron star, we might detect it as a pulsar. Pulsars are incredibly useful for physics. They're rotating with precise regularity. Some pulsars are so regular you can set your watch by them. They're nature's most accurate clocks. Astronomers use pulsars to test general relativity in strong gravitational fields, to search for gravitational waves, to probe the structure of neutron stars themselves. A young pulsar near Earth would be extraordinarily valuable. We'd be able to measure its properties with incredible precision. Its rotation rate, its magnetic field, its evolution as it ages. Young pulsars are energetic. They emit across the entire electromagnetic spectrum, radio waves, optical light, X-rays, gamma rays. They power nebulae around them. The Crab Nebula is powered by its central pulsar. Energy from the spinning neutron star keeps the nebula glowing centuries after the explosion. Betelgeuse's pulsar, if it exists, will do the same. It will energize the expanding debris, create a pulsar wind nebula, a beautiful, complex structure that astronomers will study for centuries. If the remnant is a black hole instead of a neutron star, it will be harder to detect, but still fascinating. Black holes don't emit light, but they affect their surroundings. If there's material falling into the black hole, it will heat up and glow. We might see an accretion disk, a swirling disk of hot gas spiraling into the black hole. This would emit X-rays. We could detect it. Even if there's no accretion, the black hole's gravity will affect nearby material. We could infer its presence from how the debris cloud moves. Stars passing near the black hole will have their orbits perturbed. Over decades, we could track these perturbations, measure the black hole's mass, its location. A black hole left by Betelgeuse would be one of the closest black holes to Earth, within a few hundred light years. Currently, the closest known black holes are several thousand light years away. A Betelgeuse black hole would be a wonderful target for study, close enough to see details, to make precise measurements, to test our understanding of black holes in ways that aren't possible with more distant objects. The cultural impact of Betelgeuse going supernova will extend far beyond astronomy. It will affect art, literature, philosophy, religion. Artists will respond to the event, paint it, photograph it, create installations inspired by it. The supernova will appear in poetry, in novels, in films and television shows. It will become a symbol of change, of mortality, of the vastness of the universe. Philosophers will write essays about what it means, how it affects our understanding of existence and impermanence. Religious thinkers will incorporate it into their frameworks. Some might see it as a sign, a message. Others as a natural event that fits within their understanding of how the universe works. The supernova will spark conversations, debates, reflections on our place in the cosmos. This is healthy. This is valuable, because engaging with cosmic events helps us develop perspective, helps us see beyond our immediate concerns, helps us appreciate the scale and beauty of the universe we live in. For many people, Betelgeuse going supernova will be a spiritual experience. Not religious necessarily, but spiritual. Standing under the night sky, looking at this brilliant new light, knowing you're watching a star die in real time across 650 years of distance, feeling connected to the cosmos, feeling small but also part of something vast and ancient and beautiful. This kind of experience is transformative. It changes how you see yourself, how you understand your life. The problems that seemed overwhelming yesterday feel smaller when you're contemplating the death of a star. The anxieties and worries that consume your daily thoughts fade when you're looking at something that's been traveling through space for centuries just to reach your eyes in this moment. This is one of the gifts astronomy gives us. Perspective, wonder, a sense of connection to something larger than ourselves. And Betelgeuse will give this gift to billions of people, to everyone who looks up and sees the supernova. It will be a shared moment of awe, a collective experience of wonder. And that's precious, that's important, that's one of the reasons why this event matters beyond just science. Other stars could also go supernova relatively soon. Betelgeuse is the most famous candidate because it's so prominent in the sky. But there are others. Eta Carinii is a massive star in the southern hemisphere. It's one of the most massive and luminous stars known. About 100 times the mass of the Sun. It's unstable. It had a major eruption in the 1840s. For a few years, it became the second brightest star in the sky. Then it faded. It's surrounded by a cloud of material ejected during that eruption. The homunculus nebula. Eta Carinii is expected to go supernova someday. Could be soon, could be in 100,000 years. But it's close enough, about 7,500 light years, that when it does explode, it will be visible to the naked eye. Maybe as bright as Venus. It won't be as bright as Betelgeuse will be because it's farther away. But it will still be spectacular, and it's only visible from the southern hemisphere, so half the world won't see it. But for those who can, it will be amazing. Antares is another candidate, a red supergiant in Scorpius, about 12 times the mass of the Sun, about 550 light years away. Not as massive as Betelgeuse, but still massive enough to go supernova. It's older, more evolved. It could explode relatively soon. If it does, it will be bright, maybe as bright as Venus, visible to the naked eye, another change in a familiar constellation. Scorpius would look different. The heart of the scorpion, which is what Antares means, would be gone, replaced temporarily by a brilliant supernova, then faded, gone. The constellation altered permanently. VY Canis Majoris is one of the largest known stars, a red hypergiant. About 17 times the mass of the Sun, about 3,700 light-years away. It's so large that if you put it where the Sun is, its surface would extend beyond the orbit of Saturn. It's nearing the end of its life. It's shedding mass rapidly. Could go supernova within the next 100,000 years. When it does, it will be visible to the naked eye despite the distance. A bright star appearing in Canis Major, another marker in the sky, another change to the constellations we know. These stars remind us that the sky is not static. It changes, on timescales much longer than human lifetimes usually. But it changes. Stars are born, they live, they die, and occasionally we get to witness these events. The supernova of a nearby massive star is one of those rare moments when cosmic evolution happens on a timescale we can observe. When deep time compresses into human time, when the slow processes of the universe suddenly become fast and dramatic and visible. This is why astronomers watch these stars, why they monitor them, why they hope to see them explode. Not out of morbid curiosity, but out of a deep desire to witness and understand these fundamental processes. The life and death of stars, the creation of elements, the recycling of matter through the cosmos. These are the processes that created the atoms in our bodies, that created the world we live on. Understanding them helps us understand ourselves, our origins, our place in the universe. When Betelgeuse does explode, whether it's tomorrow or in 100,000 years, the explosion will have already happened by the time we see it. This is worth pausing to contemplate. The light we see will have been traveling for 650 years. The actual explosion will have occurred in the year we see it minus 650 years. If we see it in 2025, the explosion happened in 1375, the late Middle Ages. If we see it in 2100, the explosion happened in 1450, the Renaissance. This time delay is strange to think about. We're watching the past, always, every time we look at distant objects. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star, you see it as it was 4 years ago. When you look at the Andromeda galaxy, you see it as it was 2.5 million years ago. And when you look at Betelgeuse, you see it as it was 650 years ago. We live in a universe where the past is always present in the sky, where distance and time are intertwined, where looking out is looking back. This is one of the most beautiful and profound aspects of astronomy. We're time travelers, not into the future, but into the past. Every observation is archaeology, every image is history, and Betelgeuse's supernova will be a message from the past. An event that occurred centuries ago finally reaching us, delivering its photons and neutrinos, telling us its story. This realization makes you think differently about now, about the present moment. What's happening right now at Betelgeuse? We won't know for 650 years. It could be exploding right now as you listen to this, but we won't see it until the year 2675. Our distant descendants will see it. but not us. Or it could have exploded yesterday, and we'll see it in 650 years minus 1 day. The point is, we're disconnected from the present state of distant objects. We only know their past, and this is true of everything far away. Galaxies, quasars, distant supernovae. We see them as they were, not as they are. The universe is a museum of the past, a collection of light from different eras. Some light is ancient, from the early universe. Some is recent, from nearby objects. But all of it is old. Even the light from the sun is 8 minutes old by the time it reaches your eyes. You never see the present sun, only its past. This is reality. This is physics. And it's beautiful and strange and worth contemplating. What happens after the supernova fades? After the excitement dies down and the supernova is no longer visible to the naked eye. The nebula continues expanding, cooling. Over centuries, it will grow to several light years across. The material will mix with the interstellar medium, the gas and dust between stars. This enriched material will eventually participate in forming new stars. Over millions of years, gravity will pull together clouds of gas. These clouds will collapse, form protostars, then stars. And some of these stars will form with material that came from Betelgeuse. Atoms forged in Betelgeuse's core and in the explosion will become part of new stellar systems. Maybe planets will form around these stars. Maybe those planets will have the right conditions for life. Maybe life will emerge, and maybe, billions of years in the future, intelligent beings on a planet made partly from Betelgeuse's remains will look up at their sky and wonder about the stars. They won't know their world is built from a supernova, but it will be. This is the cycle. This is how the universe works. Stars create elements, explode, the elements spread, new stars form, the cycle continues, and life, when it arises, is made from these recycled atoms. We're made from the ashes of dead stars, stars that exploded billions of years ago, and Betelgeuse will contribute to future life, future worlds, future civilizations perhaps. This continuity is beautiful. It connects us across time. We're part of a story that began billions of years ago and will continue for billions more. The supernova also reminds us of impermanence. Nothing lasts forever. Not stars, not planets, not civilizations, not us. Everything that exists will someday cease to exist. This is physics. This is entropy. This is the nature of the universe. But impermanence doesn't make things less valuable. If anything, it makes them more precious. Betelgeuse has existed as a star for 10 million years. That's a long time by human standards. But it's temporary. Soon, very soon by cosmic standards, it will be gone, transformed into something else. And that's okay. That's natural. That's how the universe evolves. And we're the same. We exist for a brief time, then we're gone. But while we're here, we can appreciate, we can wonder, we can learn, we can experience the beauty and complexity of the universe. That's enough. That's everything. The fact that it's temporary doesn't diminish it. It enhances it. Every moment is precious because there are only so many moments. Every experience is valuable because there are only so many experiences, and witnessing Betelgeuse explode, if it happens in our lifetime, will be one of those precious, valuable, once-in-forever moments. We'll carry it with us, remember it, tell our grandchildren about it. The night the star exploded, the night Orion changed, the night we watched the universe transform before our eyes. Let's explore more deeply what happens in the years and decades following the supernova, because the story doesn't end when the light fades from view. The expanding debris cloud, the supernova remnant, will continue evolving for thousands of years. In the first few years after the explosion, the debris is moving outward at tremendous speeds, 10,000 kilometers per second or more. At this speed, the cloud expands by about 2 trillion kilometers per year. That's about 200 times the distance from the Sun to Neptune. Every year, the cloud gets bigger by that much. After 10 years, the cloud might be 20 trillion kilometers across. That's over 2 light years, bigger than the distance to the nearest star from the Sun. And it keeps growing. After 100 years, it might be 20 light years across. Enormous by any measure, but still small compared to the distances between stars. As the debris expands, it sweeps up material from the interstellar medium. The space between stars isn't empty. It contains gas, mostly hydrogen, very thin, about 1 atom per cubic centimeter. That's a hard vacuum by Earth standards. But when you're talking about the volume of space the supernova remnant sweeps through, even that thin gas adds up. The expanding debris plows into this gas, compresses it, heats it. This creates a shock wave in the interstellar medium. This shock wave is visible. It glows in X-rays and optical light. We can see it with telescopes. And it tells us about the interstellar medium, how dense it is, what it's made of, how it's structured. This is valuable information for understanding the ecology of the galaxy, how material flows between stars, how star formation works, how the galaxy recycles material. Supernova remnants are laboratories for studying these processes. The expanding debris is also enriched with heavy elements: oxygen, silicon, sulfur, iron, nickel, all created in Betelgeuse's core during its life and in the explosion itself. These elements mix with the hydrogen in the interstellar medium, enrich it, make it possible for the next generation of stars to form with more heavy elements than the previous generation. This is how the universe has become enriched over time. Early in the universe, just after the Big Bang, there were only hydrogen and helium. No heavy elements. The first stars formed from this pristine gas. They lived, they exploded, they created heavy elements. Those elements spread, enriched the gas. The next generation of stars formed from slightly enriched gas. They created more heavy elements, exploded, enriched the gas further. This cycle has repeated for billions of years. Each generation of stars leaves a legacy of heavy elements for the next. Our Sun is a 3rd or 4th generation star. It formed from gas enriched by previous supernovae. That's why we have planets, why we have Earth, why we have life. Heavy elements are essential, and they all came from stars that exploded. Betelgeuse will contribute to this enrichment, will make the galaxy slightly more metal-rich. Metal is the astronomer's term for anything heavier than helium. So, oxygen, silicon, iron, all metals in this context. Over thousands of years, the expanding debris will slow down. It's running into the interstellar medium. The interstellar gas pushes back, resists. The debris loses kinetic energy. The expansion slows. Eventually, after tens of thousands of years, the remnant will fade. The energy from radioactive decay will be gone. The shock heating will diminish. The remnant will become invisible at optical wavelengths. You'll need radio or infrared telescopes to see it, and even then, it will be faint. A ghost of the explosion, but it will still be there. The enriched material will still be spreading. mixing, participating in the galactic ecosystem. After 1 million years, the remnant will be dispersed, blended into the interstellar medium, indistinguishable from the background. But the atoms from Betelgeuse will still be there, spread across light years, part of the galaxy's inventory of material, ready to participate in forming new stars, new planets, new life perhaps. This long-term evolution is harder to study than the initial explosion because it takes so long. But we can learn from other supernova remnants. The Crab Nebula from the 1054 supernova is almost 1,000 years old. We can see how it's evolved, how it's expanded, how it's interacting with the interstellar medium. We can compare it to younger remnants like Cassiopeia A, which is only about 350 years old, and to older remnants like the Vela supernova remnant, which is about 11,000 years old. Each one shows a different stage of evolution. Together, they give us a timeline, show us what happens over centuries and millennia. Betelgeuse's remnant will follow a similar path. It will expand, slow down, fade, disperse, and will track this evolution as long as we can, as long as our civilization lasts, as long as we have telescopes pointed at it. This long-term monitoring will be valuable. Each year of observation adds to our understanding, builds the data set, helps us refine models of how remnants evolve. The neutron star at the center, if it's a pulsar, will also evolve. Pulsars slow down over time. They lose rotational energy. Some of this energy goes into accelerating particles, creating a wind of high-energy electrons and positrons. This pulsar wind powers the surrounding nebula. The Crab Nebula is powered by its pulsar. The pulsar emits a wind. The wind collides with the expanding supernova debris, heats it, makes it glow. Betelgeuse's pulsar, if it exists, will do the same. Initially, the pulsar will be spinning rapidly, maybe tens or hundreds of times per second. Over thousands of years, it will slow down, maybe to a few times per second, then slower still. The pulsar wind will weaken, the nebula will dim. Eventually, after millions of years, the pulsar will stop pulsing. It will still be a neutron star, but no longer actively emitting beams of radiation. It will fade into invisibility, a dark, dense object drifting through space. This is the eventual fate of all pulsars. They wind down, stop, become inert remnants. But that's far in the future. For thousands of years after Betelgeuse explodes, the pulsar will be active, visible, a beacon at the center of the expanding nebula. Thinking about these timescales helps put human civilization in perspective. We've had writing for about 5,000 years. The Crab Nebula has been expanding for almost 1,000 years. The Vela remnant has been expanding for 11,000 years. Longer than all of human civilization. These are events that started before recorded history and continue long after our current era. They operate on geological and cosmic timescales, not human timescales, though is both humbling and inspiring. Humbling because it shows how brief our existence is compared to cosmic processes. Inspiring because we can understand these processes despite our brevity. We can study remnants that are thousands of years old, model their evolution, predict their futures. We can look at an object like the Crab Nebula and understand what it was, what it is, and what it will become. That's remarkable. That's the power of science and human curiosity. We transcend our limited lifespans through knowledge, through understanding patterns and processes that extend far beyond our individual lives. The Betelgeuse supernova will also serve an important educational role. It will inspire a new generation of astronomers. Children who see the supernova will remember it for the rest of their lives. Some will be inspired to study science, to become astronomers, to dedicate their careers to understanding the universe. This has happened before. The Apollo moon landings inspired a generation. The Hubble Space Telescope's images inspired another. Betelgeuse's supernova will inspire the next, and that inspiration will have lasting effects. Those inspired children will grow up, become scientists, make discoveries, train the next generation, who will make more discoveries. The impact compounds. One spectacular event can change the trajectory of human knowledge, can catalyze advances that ripple through time. We can't predict exactly what will come from Betelgeuse's supernova, what discoveries, what technologies, what insights, but we can be confident that it will matter, that it will advance human understanding, that it will contribute to our collective knowledge in ways we can't yet imagine. There's also something to be said about luck. We're lucky to be alive at a time when Betelgeuse might explode. Humanity has existed for a few 100,000 years. Betelgeuse has been a red supergiant for maybe 100,000 years, maybe longer, maybe shorter. But the point is, there's overlap. We exist during Betelgeuse's final phase. If we'd evolved 1 million years earlier, Betelgeuse would still be a normal star, not ready to explode. If we evolve too late, if we go extinct before Betelgeuse explodes, we'll miss it. But we're here now, in the right window. This is fortunate, not guaranteed, just fortunate. And it reminds us that timing matters. We happen to exist during an era when the universe is interesting in particular ways. Stars like Betelgeuse are dying. Black holes emerging, galaxies are colliding. All of these events are happening now in this epoch of cosmic history. Other eras might be less eventful. The early universe was chaotic but simple, just hydrogen and helium and the first stars. The far future will be cold and dark. Stars will have burned out. Black holes will have evaporated. Nothing much will happen. But now, in this middle period, the universe is rich and complex and dynamic. We're lucky to be here for it. This raises interesting questions about observers and the universe. Does the universe care that we're watching? Does it matter that we're here to witness Betelgeuse explode? Physically, no. The explosion will happen regardless of whether anyone sees it. The universe doesn't need observers. But philosophically, observers matter. The universe without observers is just events, things happening. But with observers, those events have meaning. They're witnessed, understood, appreciated. We give the universe meaning by observing it, by trying to understand it, by creating models and theories and stories about what we see. Betelgeuse will explode. That's physics. But the explosion becomes meaningful because we're here to see it, to study it, to be awed by it. This is our role. Observers, witnesses, meaning makers. We're the universe becoming conscious of itself, looking at its own processes, understanding its own nature. That's profound. That's special. And Betelgeuse's supernova will be one of those moments when we fulfill that role, when we observe and understand and appreciate a fundamental cosmic process unfolding before us. Let's also consider what amateur astronomers will contribute. Professional astronomers have the big telescopes and the sophisticated instruments, but amateur astronomers are valuable too. They have flexibility, they can observe every night, they can respond quickly to changes. When Betelgeuse explodes, thousands of amateur astronomers around the world will point their telescopes at it. They'll take images, record spectra, measure brightness, send their data to professional astronomers. This crowdsourcing is important. It fills gaps, provides coverage when professional telescopes are pointed elsewhere, adds redundancy. If one telescope fails or has bad weather, others are still observing. The supernova will be monitored continuously by a global network of observers, professional and amateur working together. This collaboration has happened before with other astronomical events. Supernovae in other galaxies, comets, asteroid occultations. It works well, and for Betelgeuse, it will be essential. Everyone will want to contribute, to be part of this historic observation, to help gather data that advances human understanding. The data from all these observations will be archived, made publicly available. Future generations will be able to access it, analyze it with new techniques, learn from it in ways we can't anticipate. This is standard practice in astronomy. Data is preserved, shared, made available to anyone who wants it. This openness accelerates discovery, allows unexpected findings. Someone analyzing old data might notice something the original observers missed, might make a connection that wasn't apparent at the time. Archival data is valuable, and Betelgeuse data will be especially valuable because it will be comprehensive. Every wavelength, every time interval, high resolution, well calibrated, documented. It will be a treasure trove for future astronomers, a resource that will be used for generations. There's one more aspect worth exploring, and that's how the Betelgeuse supernova will affect our understanding of our own origins. We know that the atoms in our bodies came from stars, hydrogen from the Big Bang, everything else from stars. But which stars? What types? How long ago? These are harder questions. We can trace the general story. Early stars created the first heavy elements. Those elements were incorporated into later generations of stars, including the Sun. The Sun formed from a cloud of gas enriched by previous supernovae. Earth formed from material in the solar nebula. Life arose on Earth using those atoms. We're made from recycled stardust. But the specific stars that contributed to our atoms are unknown, lost to history. We can't identify them, but we can study similar stars. Stars like those that exploded billions of years ago to create the atoms we're made of. Betelgeuse is such a star, a massive star that creates heavy elements and will distribute them via supernova. By studying Betelgeuse, we learn about the stars that made us, the processes that created the atoms in our bodies. This is personal. This is about our origins, where we came from, what we're made of, and understanding Betelgeuse's explosion will deepen that understanding, will help us appreciate our connection to the cosmos more fully. The technology we'll use to observe Betelgeuse also deserves attention because it represents the cutting edge of astronomical capability. The James Webb Space Telescope, if it's still operational when Betelgeuse explodes, will observe in infrared. This will let us see through the dust that surrounds Betelgeuse, peer into the ejecta, study the chemical composition with unprecedented detail. Webb's spectrographs can identify individual molecules, individual isotopes. We'll be able to map exactly what elements were created and in what quantities. This is fundamental data for understanding nucleosynthesis, the creation of elements in stars. Webb can also observe the shock wave as it expands through surrounding material. Watch how it heats and compresses gas. Study the physics of shocks in real time. This is valuable for understanding many astrophysical phenomena: shocks in supernova remnants, shocks in stellar winds, shocks in galaxy collisions. All of these involve similar physics. Betelgeuse will be a perfect laboratory for studying it. The Hubble Space Telescope, if it's still operating, will observe in optical and ultraviolet. Hubble's imaging is extraordinarily sharp. It can resolve tiny details, track the expansion of the debris with precision, watch for asymmetries, clumps, jets. All of these tell us about the explosion mechanism and the structure of Betelgeuse before it exploded. Hubble can also measure the brightness very accurately, track the light curve, see if it follows predictions or shows unexpected behavior. Every deviation from the predicted light curve is a clue, a hint about what's happening inside the expanding fireball. Hubble has observed many distant supernovae, but Betelgeuse will be different. So much brighter, so much larger, so much closer. Hubble will capture images that become iconic, that define this event for generations. The expanding debris, the central pulsar, the surrounding nebula, all in exquisite detail. Ground-based telescopes will contribute too. Large telescopes like the Very Large Telescope in Chile or the Keck telescopes in Hawaii will observe with adaptive optics. This corrects for atmospheric turbulence, sharpens the images. They can track rapid changes, take spectra every night, monitor how the spectrum evolves as the ejecta expand and cool. Different elements become visible at different times. Hydrogen first, then helium, then oxygen, silicon, iron. By tracking when each element appears in the spectrum, we learn about the layered structure of the ejecta. What elements are on the outside, what's deeper in, how they're distributed. This maps out what happened during the explosion, how material was ejected, how it mixed. Radio telescopes will observe the expanding shockwave. When the shock plows into the interstellar medium, it accelerates electrons. These electrons emit synchrotron radiation at radio wavelengths. Radio telescopes can detect this, map the shock structure, see where it's bright, where it's dim. Bright spots indicate denser regions of interstellar medium. Dim spots indicate voids. This maps the environment around Betelgeuse, tells us about the star's history, how much mass it shed before exploding, how that mass was distributed. Did it blow a bubble in the interstellar medium? Did it create a wind? Radio observations will answer these questions, and they'll continue for years, decades. As the shock expands and interacts with more distant material, radio telescopes will keep watching, keep mapping, keep learning. X-ray satellites will see the hot plasma. The shock heats material to millions of degrees. At these temperatures, the gas glows in X-rays. X-ray telescopes can see this glow, study its spectrum, measure the temperature, the density, the chemical composition. X-rays tell us about the most energetic parts of the supernova, the hottest regions, where particles are being accelerated to high speeds, where cosmic rays might be created. Supernova remnants are thought to be the main source of cosmic rays in the galaxy, high-energy particles that fill interstellar space. Betelgeuse might create a new population of cosmic rays, and X-ray observations will help us understand that process. Watch it happen in real time. All of these telescopes and instruments will work together. a multi-wavelength campaign, coordinated observations, data shared immediately. Scientists from different disciplines collaborating. This is modern astronomy at its best. Not isolated observers making individual discoveries, but networks of people and instruments working together toward common goals, understanding the universe, answering fundamental questions, pushing knowledge forward. Betelgeuse will showcase this collaborative approach, and the results will be better because of it. More complete, more comprehensive, more insightful. No single telescope can see everything, but together they can build a complete picture, and that picture will advance our understanding in ways no single observation ever could. The theoretical work will be equally important. As data comes in, theorists will compare it to models. Are the models right? Do they predict what we observe? If not, why not? What needs to change? This back and forth between observation and theory is how science progresses. Observations test theories. Theories predict observations. When they agree, we gain confidence. When they disagree, we learn something new. Betelgeuse will test our theories of stellar evolution, supernova explosions, nucleosynthesis, and shock physics. And inevitably, there will be surprises. Things the models didn't predict, anomalies, unexpected features. These are the most exciting moments in science, when nature reveals something we didn't anticipate, when our understanding proves incomplete, when we're forced to think harder, to develop new ideas, to expand our theories. The surprises are what drive discovery, and Betelgeuse will almost certainly surprise us. The computational work behind these models is staggering. Simulating a supernova requires supercomputers, massive computational resources. The physics is complex: hydrodynamics, radiation transport, nuclear reactions, neutrino physics, magnetic fields. You have to track billions of particles, follow their interactions, solve equations that describe how they move, heat up, cool down, react, emit light. And you have to do this for a three-dimensional star over timescales from microseconds to hours. The computational cost is enormous, but it's worth it, because these simulations let us predict what will happen, let us test our understanding, and when Betelgeuse explodes, we'll compare the observations to the simulations, see how well we did, learn where our models are accurate and where they need improvement. This iterative process, simulate, observe, compare, improve, is fundamental to science. And Betelgeuse will be a major iteration, a major test, a major opportunity to improve. There's also a public engagement aspect to consider. When Betelgeuse explodes, it will be global news. Media coverage will be extensive. Scientists will be interviewed, asked to explain what's happening, why it matters. This is an opportunity to share astronomy with the public, to excite people about science, to show them that the universe is dynamic and fascinating and worthy of study. Many scientists relish these opportunities to communicate their passion, to share their knowledge, to inspire others. The Betelgeuse supernova will be one of the greatest public engagement moments in the history of astronomy. Millions of people who normally don't pay attention to astronomy will suddenly be interested. They'll want to know what's happening, how to see it, what it means, and astronomers will be there to explain, to guide, to share the wonder. This communication is important. It builds public support for science, inspires future scientists, creates a scientifically literate population. all valuable outcomes that extend beyond just the immediate excitement of the event. Social media will play a huge role. When Betelgeuse brightens, images will flood Twitter, Instagram, TikTok, whatever platforms exist at that time. Amateur astronomers will share their photos. Professional observatories will release stunning images. People will post their reactions, their awe, their questions. This crowdsourced documentation will be remarkable, a snapshot of how humanity responds to a cosmic event, how we share wonder, how we collectively experience something extraordinary. And it will be preserved, archived. Future historians studying this era will be able to see exactly how people reacted, what they thought, what they felt. This is unprecedented. Previous generations didn't have these tools. When Kepler's supernova appeared in 1604, there were books and letters, but not global instant communication, not millions of people sharing their perspectives simultaneously. Betelgeuse will be the first supernova of the social media age, and that will change how we experience it, make it more immediate, more shared, more connected. Educational resources will be created, planetarium shows, documentaries, museum exhibits, online courses, all focused on Betelgeuse and supernova in general. These resources will reach millions, teach them about stellar evolution, nuclear physics, the origin of elements, the beauty and power of nature. This education has lasting value. People who learn about Betelgeuse will carry that knowledge forward, share it with others. Some will be inspired to learn more, to study science, to pursue careers in research or education. The ripple effects are impossible to quantify, but certainly significant. One spectacular event can change lives, can alter trajectories, can create opportunities that didn't exist before, and Betelgeuse will create many such opportunities. There's also economic impact. Observatories will receive increased funding. Public interest translates into political support. When people are excited about astronomy, politicians respond. They fund research, support missions, invest in infrastructure. Betelgeuse could lead to the construction of new telescopes, the funding of new missions, the training of more scientists, economic benefits that extend for years or decades after the event. This might seem cynical, tying economics to something as profound as a supernova, but it's realistic. Science requires resources, funding, support, and public interest generates that support. So, while we appreciate Betelgeuse for its scientific and aesthetic value, we can also acknowledge its practical benefits. The ways it might help astronomy as a field, help science more broadly, help society by advancing knowledge and inspiring people. The legacy of Betelgeuse will be long-lasting. Centuries from now, when the remnant is faint and dispersed, people will still remember the supernova. It will be in history books, in cultural memory, a defining moment, an event that marked an era, and the data collected will still be valuable, still analyzed, still producing discoveries. Because astronomical data doesn't expire, it remains relevant, sometimes more relevant as our understanding improves. Old data viewed with new insights can reveal things the original observers never imagined. So, the Betelgeuse observations will live on, will continue contributing to science long after the event itself has faded from living memory. This permanence is special. Most human endeavors are temporary, but knowledge, once gained and preserved, persists, compounds, builds on itself, creates a legacy that transcends individual lives and generations. Betelgeuse will be part of that legacy, a contribution to humanity's collective understanding of the universe. Thank you for exploring Betelgeuse and its impending supernova with me. If this journey into stellar death expanded your sense of wonder at the universe, a like or subscribe really helps the channel keep investigating these profound cosmic stories. And remember, every time you look at Orion, you're seeing Betelgeuse in what might be its final years, or its final centuries, or it might have already exploded and we're waiting for the light to arrive. The universe is full of mysteries, full of events happening beyond our sight. And someday, maybe soon, maybe distant, the mystery of Betelgeuse will be revealed. The star will explode, the sky will light up, and we'll be there to witness it, to marvel at it, to learn from it, to be transformed by it. Good night, and may you never look at Betelgeuse the same way again.